Good day, everybody. So let's take a look at some topics of the morning. We'll take a look at several select ones in the form of problems, as usual. So what we're going to do is start with the hydration of alkenes. That will lead us to the production of alcohols, right? So if we consider this topic in like broad strokes, so to say. But now we're going to take a look at some specific things, which are reactions between the water in the presence of H2SO4 or sulfuric acid as the necessary additive to make this reaction possible. And of course, we're going to hydrate alkenes, right? So like one thing to remember is that sometimes the atoms which constitute the double carbon-carbon double bond are not equivalent, right, in terms of their surroundings, right? So to say, for example, if you have two butene, which at this point you should be able to quickly draw on the piece of paper as you hear the name, right? So in that case, if we just consider two butene, for instance, which looks something like that. So we have our molecule of two butene, right? So that's the one. So basically 4 carbons, and then carbon number 2 from this end or that end. So either way, so the double bond will start and finish at carbon number 3, right? So in this case, if you look at this carbon here, so this is going to be just like read as CH carbon, right? So it has 4 bonds total. This is also CH, so the molecule is pretty symmetrical as far as those kind of carbons sp2 hybridized carbons, by the way, are concerned. So no matter where we are going to add OH and H, we're going to have the same result, right? And the result after hydration, of course, will look like this, like OH, right? So if you try to redraw that, so maybe you are going to get something like this. But if you compare the top and bottom molecule, they are the same. So this is just essentially flipped, right? 180 degrees and top to bottom. So yeah, but as the same molecule, they kind of like superimposable, right? If you try to align them on one another, then you will have the perfect alignment. So you're going to have ultimately the alcohol here, right? We didn't look at the nomenclature yet. So yeah, but it's going to be, so if you look at some kind of like parts, you can make an educated guess, right? Because at this point, you know that, okay, well, 4 carbons in a chain will have the root, which is going to be something like but, right? So BUT, so from butane, so which is our like fundamental alkane. So, but then as we know, like alkanes possess those kind of CH bonds. You can remove the hydrogen, for example, and substitute it with something more exciting, more functional, right? Pun intended, because literally you're making here the functional group, which is going to be like COH, right, together with this carbon. So COH will constitute the alcohol in organic chemistry. So you're going to have some sort of like alcohol from the like alkane. So we at this point remember that alcohols will have the suffix a, not a, but ol, right? It's going to be some sort of butanol, right? So and then since OH is going to be on carbon number 2, it's going to be, by the way, 2-butanol, right? So speaking of names, we're jumping ahead of the train a little bit, so, but it's okay. So again, here, if you look at this, so lots of parts are already known, right? So this butane, right? So it's going to be the stem or the root that signifies that you have 4 carbon chain, right? So then OL suffix will constitute, will be related to alcohols, right? So that's kind of like the sign that you have an alcohol. 2, that's going to be the position where this like OL group is related. What's the OL group? It's the OH group, right? So it's kind of, so why do we call it OL? Because if you have the OH group attached to the carbon in the chain, right, you are going to have an alcohol, right? So that's why like OL can be associated with the OH. So you can also call OH the hydroxy group, right? So hydroxyl, so that's all kind of like synonymous with the OH group. So yeah, or just OH if you forget all the names, but it's a good idea to just know hydroxy, right? Hydroxy group, it is OH or hydroxyl. So it's a very, very common group. So we'll encounter this a lot. So basically on carbon number 2, right? 1, 2, 3, 4. On carbon number 2, we'll have the OL group, which again is translated structurally to the OH group. Anyway, so that's what we're going to make after hydration. Now let's take a look at the hydration itself. So today we have several examples just to get the minds going, right? Of course, there could be like potentially a million or thousands of possible hydration reactions. We cannot go over all of them because we physically don't have enough time for that, but hopefully these examples will spur your creativity, so to say. So now let's take a look at some of them. So for example, here we have an example like that. So let's say CH3, CH2, carbon, methyl, so double bond, CH2, right? So that's your example here. So we are going to show the bonds, right? So now this, imagine we are going to add water. So in the presence of H2 SO4 as a necessary additive. So what's going to happen is that we are going to deal with the hydration reaction. Hydration, that's when we add the molecule of water to the alkenes, right? So this reaction falls under the addition reactions category, means that the entire like HOH structure or H2O will be added to this molecule of alkene, right? And then you will have basically the these particular alkene atoms, however many carbons and hydrogen there are, plus you have H2O total, right? So 2 more H's and 1 more oxygen. So will be resultant then in this structure. So, or will reside rather in this structure. So you're going to have the alcohol, right? So here we have the non-symmetric. It's not like a 2-butene anymore. It's sounding more complicated. So we have, as we call them, let's say the left carbon and the right carbon, just in this particular lingo of ours, right? So now in this case, so we also remember, so one of the pieces of information about this hydration reaction is that it follows Markovnikov's rule, right, which says that the hydrogen from the water will go to the carbon amongst the sp2 carbons. The hydrogen will go to the carbon with more hydrogens, basically, right? So if we look at this structure, we can clearly see that the left carbon has 0 hydrogens, the right carbon has 2 hydrogens. So consequently, the hydrogen from the water will go to this carbon, right? So let's just say like hydrogen will go to this carbon. So OH, which is going to be apparently O and H, will have to go to the left carbon. So I show it as if it goes from the oxygen, but you need to understand that, yeah, the water is kind of split into 2 parts, H and OH, which will be associated with, respectively, the carbon with more hydrogens and the carbon with less hydrogens, right? So what do I mean by that? So by that, you can like try to go ahead and then draw that, right? So yourself whilst I'm rambling. So, but now we are going to show the results. So let's show it here. CH3, don't leave it. I mean, don't touch it. So it stays, right? So this is kind of the unreactive part. Then C, then also we're going to break this kind of like pi bond, right? So we'll show the like scission with the squiggly line. So the sigma bond will remain, so CH2. So just like show basically gradually changes in the molecule. So then we'll have those available electrons, which were separated, as some people say, right? So from the like previously existing bonding, and here we go, right? So then the hydrogen from the water, so water can be represented as HOH. If you think about it, right? So because we can see this way the bonds, so it's okay to show that as HOH. right? So we'll just kind of like imply or like show explicitly there's a bond between hydrogen and OH, right? So then you can see those are electrons, right? So on the hydrogen and oxygen. So that can be used to make new bonds. Oops, I made a doo-doo. So, or a mistake, whatever it's called in slang terms. All right. So, or maybe it's something else. All right. So anyway, so Control Z. Okay. Yeah, that's right. So here we go. So then the hydrogen from the water, so let's maybe like show it as H with the dot, will go to the carbon with more hydrogens. So 2 hydrogens, 0 hydrogens, right? So hydrogen from the water will go to more hydrogens area. So then here we go. So we basically make the CH3 group, right? So CH2 now is connected to H. So then OH will have to be left over and it will be connected to the more substituted carbon, right? So as we call it, so because this carbon has connection to 1, 2, 3 carbons. The right carbon has only connection to 1 carbon, so it is less substituted. That's another way to like think about this Markovnikov's rule, right? Whatever floats your boat, so to say. So, and here we go. So that's going to be our 2 new bonds that we form. We form the alcohol. So you look at this molecule, it looks like basically the branched alkane of some sort, right? So with the OH group attached to that, with the hydroxy group, hydroxyl, right? And then we have this like COH formation, which will be a sign of the like alcoholic functional group. The alcohol functional group will be now present. All right, so that's your thing, right? So you form the product. So you showed here all the necessary parts, such as like the reactants, alkene and water, the necessary like additive, H2SO4. So don't forget to show that. It's kind of like necessary for hydration reactions. You show the product, and yeah, you predicted also according to the Markovnikov's rule, because theoretically you can like put the OH either to this carbon or that carbon, right? So it can go anywhere. So, but here we can decide where it will go. And then if you look at this, so this molecule is not as symmetric as a 2-butene, for example, that we talked about earlier. Here we have like 2 carbons which are different, right? So those sp2 hybridized carbons. And theoretically, so OH can go like either way, to the left or to the right carbon, right? And if you think about it, you will have different attachments, right? So if OH is going to be attached to the like L carbon, that's going to be our kind of like major product. But looks like we might have also some impurity, right? Something to keep in mind. So because oftentimes reactions, no matter how selective, right, in terms of where the things go, right? So where they select to go, no matter how selective they are, so you can have some kind of like error going on, right? And then you will have the like impurity, maybe like 1%, 2%, whatever, right? So it can still be formed. So just kind of like don't rely 100%. Like the rule will be having 100% purity, right? Oftentimes there is some impurity going on. So and then, yeah, depending on where the OH group will be attached, you will have different isomers, right? So if OH is on the left carbon, it's not going to be the same compound exactly as when the OH is ending up on the right carbon, right? So you'll have the isomers. So, but according to the rules, so we're going to get this product. It's going to be the only one, kind of use absolute terms here. So, but in reality, so oftentimes, yeah, there are rules, right? So where like supposedly we are going to like predict the major product, but keep in mind that those things are not absolute in real life situations, right? And we need to consider the impurity formation. Okay, so then what else? So moving on, so let's have a look at some other examples here. So maybe we're going to erase everything and go ahead and then do and then take a look at some like cyclic alkene, right, which will be actually symmetrical, and it's going to be a little bit easier molecule to deal with, because there we don't have to apply the Markovnikov's rule, by the way. So when we have something like this, right, so it's going to be a cycle, right? So that's going to be a cyclic alkane, essentially. So not like a straight chain, right? It is a cycle hexagon. And then sometimes we can have a double bond here. If you look at this compound, right, so you can write it out, transform it, and then just show the carbons in the double bond because that's where the hydration will be happening. So CC, double bond, and then, yeah, this is our carbons and hydrogens, right? So we follow the rules. So the carbon is tetravalent. So then once we are going to add H2O in the presence of H2SO4 here, so we are going to engage these two carbons in the reaction, right? Everything else is just CH2, 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 and CH2, right? So those carbons are, if you look at them, they only will possess single bonds, right? 4 single bonds each. So these are sp3 hybridized carbons, 1, 2, 3, and 4. So they will not be participating in the hydration reaction. So yeah, only these ones. So sp2, sp2, right? If you look at the patterns also, like, just again, try to like review things, right, as you like look at new topics and new molecules. But if you think about it, there is like nothing new in terms of the building blocks, right? So you have seen everything in the past. You have seen like those CH2s, right, which are called like methylenes. You saw CHs with a double bond, which are part of alkenes. So, and yeah, so just kind of like different combination of those blocks gives you like different looking structures of compounds, right? So, and then, yeah, no matter where you're going to attach H or OH, you are going to get the same product at the end of the day, right? So here we go. Let's show that. So now we are going to have CH with an OH here, for example, single bond, right? So because the pi bond here will be broken, we'll show it with a squiggle line. So then again, so here we have it. So CH and the hydrogen will be attached. So the OH and hydrogen, which are underscored, came from water, right? And you have some sort of a cyclic alcohol, right? So if you switch literally OH and H here, these ones on the outside, in terms of their positions, you will get the same compound, right? So those compounds will be kind of easily imposable on one another. So nothing new. So then those basically, if you look at this, there is symmetry, right? So this CH and that CH have kind of the same substitution patterns, right? So they don't have like more or less alcohols, no, more or less H's. So compared with one another, so they are equally substituted, right? So they have attachment to two other carbons. So no matter where the OH goes here, that carbon or the bottom carbon, you will have the equivalent structures, right? So that can be kind of like, if you look at this, right? So if you look at the molecule this way, right? If you decide to put the OH on the bottom and then that H will be on the top, right? It's nothing more than this molecule kind of like grabbed by the OH and flipped 180 degrees, like inside or kind of like out and then into back the whiteboard, right? So just 180-degree flip around this axis, around this line, right? So then you're going to get the same, this compound, right? So it's going to be the same compound. Equivalent, two molecules are equivalent, they're equal to one another. So anyway, just something to keep in mind, like symmetry versus no symmetry. So, and then again, so the previous skills, such as like being able to write the expanded structure will help right here to identify like how many carbons and hydrogens there are on a particular carbon, right? So in terms of attachment to it. So then what else? So now let's take a look at something more advanced a little bit. So because we can have this moment here. So we're going to consider, let's continue that with as a problem. Problem 2, perhaps, right? So what do we have here? So we have this structure. So it's kind of, I think it is a natural product. So that looks like this. So it will have two alkene groups, if you assess the situation here. So, and then here we go. So that's gonna be our molecule. So now we're going to add somehow two H2O molecules to that structure, right? So again, in the presence of H2SO4, this reaction will go. So now let's take a look at what could happen here. So again, so we'll have two like alkene centers. So that's 1 and 2 here, right? So two alkene centers. So and then, yeah, so we can attach like HOH parts to all of those, right? Granted, we have two H2O molecules, so theoretically we can have like one HOH going here, another HOH going this way, right? So like two like centers of the like alkene, two alkene centers basically. So then what else? So now we're going to take a look at the carbons here. So carbons here are clearly not the same, right? So for example, this carbon has the attachment to two other carbons, right? And it has 0 H's. This carbon here has the attachment to only one carbon and it has two H's, right? So now you can sense that we are kind of like talking about this Markovnikov's rule, right? So which is going to be like, okay, well, the hydrogen from the OH will go to the carbon with more hydrogens, right? So again, so if you look at the top structure, top center, right? So here we have the carbon with 0 H's, right? 1, 2, 3, 4, 4 bonds. So it's again done, right? It's burnt out, right? In terms of attaching H's to that. It cannot attach any more H's because it already has 4 bonds to that, right? Shown explicitly. So yeah, then we need to understand, then we cannot like enforce the fifth bond to attach like an H, right? So that's not going to work. So because the carbon cannot have 5 bonds. So then this carbon, however, will have the H here, right? So because we explicitly see 1, 2, 3, sigma pi sigma, 3 bonds, and then we can like understand that, okay, well, the carbon has to have like 4 bonds, right? So we are going to attach something which is implied, right? Implied means not shown, but by convention, we know that carbons and H's are implied, right? So we cannot randomly attach, for example, like fluorine here, right? Because it would be shown otherwise, right? So if you have fluorine here, then it would be signified as such, right? So, but here we go. So we have like only one H which we can attach because this is not shown, but we need to like beef up the fourth valence with something, and it's going to be only H, right? So now you have your decisions: 0 H's, 1 H, 0 H's, 2 H, right? So that's where the H's from the water molecules will go. And then this will help us make our final product. So which is going to be looking like this. So I'm breaking the pi bonds everywhere, and I leave the sigma bonds only. Okay, great. So now that's critical here. All right, so H will go to where like there is more H's. So let's maybe make them different colors because why not? It's Friday, right? So the H from the water, let's say they are blue, right? So we have our HOH, just kind of make a like snippet here or excerpt, whatever it's called, right? And then we have here our new H, right? So this in the black font, we will have our old H, okay? So then the OH, which will show in blue, will attach there, okay? So it will be like, in other words, right, will be attached, the OH will be attached to the more substituted carbon, right? So this carbon here has connection to 1, 2, 3 carbons. This carbon here is less substituted because it's only connected to 1, 2 carbons, right? So less substituted thereby. So that's our like first alcohol. And then the second one, so same token, right? So the blue H's, they will go here to more H's, right, to carbon with more hydrogens. So, and then the OH will be end up here, right, will end up here because it's going to be on the carbon, which is more substituted. It's attached to 1, 2, and 3 carbons, right? So this carbon is less substituted. It cannot get the OH because it's only attached to 1 carbon. That's it. 1 is less than 3. So yeah, this is your like big alcohol, right? So if you like look at this, ask yourself, what can I say like in those like legitimate terms, right, about these compounds? So it looks like it has a cycle, right? So you can recognize this as a cycle. So this hexagon, so that it has like lots of like alkane character, right? Lots of alkane chains and function groups, right, in like general terms. So then it also has like this COH formation and another COH formation. So it has two alcohol functional groups, right? So then you can think about polar bonds, right? So if like somebody asks you, oh, show where the non-polar and polar bonds are here, right? So you can recognize a bunch of CH bonds and call them like non-polar because the CH bonds are by convention are considered non-polar since the electronegativity difference between the values of electronegativity for carbon and H are too close, right? So it's like too small of the difference. So, but OH bond, for example, is polar, right? So carbon O bond is polar. So, and then you can like think about like just like take a look at the periodic table, right? So there's a dynamic periodic table, and you can compare based on the electronegativity differences, right? So just like do your research if you like want to become a little bit more advanced, right? So which bond will be more polar, like CO versus OH, right? Compare the electronegativity differences between CO and OH, right? And then like make your decisions, and then look at maybe electronegativity difference between C and H, right? And then you will see how the difference in electronegativity is kind of like impacts the polarity. But yeah, it's a little bit more of like getting into the weeds of that. So if you want to do that, then you can. So yeah, it's always good to get into those details, but again, not too much, right? So we need to have the boundaries. So anyway, considering our commitments, so considering other commitments. All right, so that's the one here. Now let's move on to polymers, right? So we're going to go kind of like from the monomer to polymer and from the polymer to monomer, right? So that's going to be our other problem. So real brief. Here, okay, so 1 p.m. So we have about half an hour, I would say, not to overwhelm anybody. Okay, so here we go. So yeah, polymer formation. So yeah, let's take a look at the propene. One propene, right, or just propene, because not anywhere else. You can, no matter where you put the double bond, it's going to be propene anyways. So and then if somebody hears this word, they will be able to like unambiguously draw the structure of like one of just propene, right? So it's going to be basically propane essentially, but it lost two hydrogens and became an alkene. CC double bond is now there. So we have the alkene called a propene, right? If you put a double bond here or here, it's going to be the same compound. So you might as well just call it propene. The designation, the number is not necessary, right? So where the like double bond starts, right? So no matter where you put it, you will have the same compound, right? So just propene. So now this compound can be turned into the polymers. So remember, so if we have, for example, 1,000 molecules of proteins, so we can put them together. How, right? So via the formation of the covalent bonds, right? So let's take a look at this like pi bond here and show it in color maybe, right, with those like electrons. So apparently, so under certain conditions, so this bond can be broken. So, and then this can be done, so like in a particular fashion. So for let's say 1,000 molecules of propane, let's say, right? So now they will become connected, right, via covalent bonds between carbons, right, of those individual propane molecules to make a polymer, right? So then let's take a look at how they are formed, right? So for here, we can show the things like that, right? So this kind of like CH-CH3 bond stays intact, right? So, and then oftentimes, so what happens is that it's kind of convenient to like put it down and then make it point like away from like the like chain, right? Which is going to be actually built upon the bond formation. So, and here you have it, right? So you have a bunch of those propene molecules. Maybe if you have like some time, right? So draw like 10 of them, right? So then you will like practice your polymer writing skills. So here I have both the strained time and space, right? So, but still we can show something, right? So then we're going to show those red electrons, which participate now in the bond formation. So there they are, right? So that we can kind of show them outside a little bit of the molecules, and then we're going to connect them because we're going to connect those molecules with one another, right? So the electrons kind of like welcome, right? The formation of the bonds between them. And here we go. So let's show them with the new bonds with the like blue color, right? Or something. So that's the new bonds which are formed. So and then you connect two molecules, right? So then you connect other two molecules. and so on, right? And then here you can see the chain, right? So this will be connected to another molecule, as you can imagine. Maybe draw it yourself, what's going to be beyond those squiggly lines, right? So of course, don't forget that the sigma bond, right? So that kind of like the black one still remains. So let's show it here as such. That's a carbon-carbon bond inside the individual molecule of that monomer, right? So, and that molecule will prevail. So that bond will prevail. So that's it. So also not it yet, right? So we have to have our like CH2s, right? Of course. So they don't like just magically disappear. So CH2. So that's going to be our CH, CH2 and CH. So don't kind of like forget the parts, right? So that will kind of like basically fall under this philosophy or balance in the like equation, right? So the like hydrogen atoms just don't like disappear, right? Don't forget them. So they will stay. But here we go, right? So CH2, CH, CH3, so CH2, CH, CH3, right? So this kind of like building block or a monomer, as we call it, so is now used to connect with other like 999 monomer molecules, right? And that will result in the production of the polymer molecule, right? So which will have, as you can imagine, a high molecular weight, right? So the high molecular weight will translate into the higher mass in grams of a mole, right? So 1 mole is like the Avogadro number of particles, right? So it's going to be like pretty heavy. So pretty heavy molecule, right? So there is a question. So how you can tell a difference whether it's a monomer or polymer? Well, just by the look of that, right? So if you look at this molecule, it's going to be like a short one. So, and then in our considerations, we were also looking at the monomers, which are alkenes, right, in their nature. If you look at the polymers, so yeah, that's a very good question, actually. So the polymer will look different, right? So basically, it's like a longer chain, so you will have to have several monomers in it, right? So definitely more than one. So, and then typically it's going to be like at least 10, right? So there are some kind of like more or less cloudy guidelines. So, but you need to have like a bunch of molecules, and a bunch means you will have like maybe like 10, 100, 1,000, right? So it will be kind of like shown in the structure. So also the polymer will now become an alkane. If you look at that, it doesn't have any more double bonds in its structure, right? So it can have double bonds, but maybe we need to start with like other monomers, such as maybe like alkene, right, which will like break one of the pi bonds, and the other sigma and pi bonds will remain, right? So, but and still like the bonding pattern will be different, right? Will be different. So we have the monomer here that contains double bond. If you look at the polymer, it doesn't have like any more double bonds. And then sometimes what's happening, right? So we can also say how many monomers was used, right, in the chemical reaction. So maybe it's like 3, right? So let's just like imagine that we're making like a very short polymer, right? So somehow, so like 3 monomers are used in this molecule, right, to make a molecule of the polymer, right? And then we're going to have to put this kind of like 3 connected molecules into the parentheses, like so, and then we'll put the n number underneath, or in this case, it's going to be 3, right? So basically, this is your n. That's going to be the number of the monomers in the chain. It's going to be like generally called n, right? N can be different. N can be like equal to 100,000, right? And then it will translate here as a subscript, right? So that's going to be still our number n here. So in this case, it's going to be equal 3. So, but you might as well say, well, so we are going to have perhaps so here we kind of show them all, right? So these are all like 3 molecules. In this case, it's actually technically, strictly speaking, not necessary to show the number, right? So because we here have the proper balance, right? So we have 3 molecules of the monomer, and then here we go, 1, 2, and 3 molecules are connected already, right? So into the polymer chain. So another way to kind of like look at this is what if you have maybe 100, let's say, right? So 100 molecules connected, right? So let's make this example. We're going to erase 3, make it 100, right? So what you're going to show in your like polymer structure, right, and to tell them apart, so it's going to be something like this. So the bond still will be broken, right? And then essentially we need to show the formation of this like alkene chain. So you can, instead of showing all the 100 molecules connected into the chain, you can show the polymer structure like so. So just say 100 molecules, right? And then show here 100 and draw one molecule, right? So that's what we have here if we split this thing into parts, right? So now we're going to show the same molecule with the broken bond, right? Red electron will signify the broken bond. And then those electrons will be able to form the further covalent bonds with other monomers, right? And we show basically half of this line representing the covalent bond. It's 1 electron and half of the line approximately, right? So, yeah, that's right. So, and then here we also have the carbon with the electron and half of the line showing the bond. And then we show the like parenthesis right here that will be kind of in the middle of the line showing the bond. And then we'll put the subscript of 100, right? Basically, you have 100 molecules of this kind, and then you have 100 molecules of this kind connected into the polymers. So again, by the look of the left and right side, we have the differences, right? So significant differences. So basically, that's how you can tell the monomer and the polymer apart. So good question. So, but anyway, so that's kind of like it for now. So now let's take a look at like other things, right? Such as, for example, aromatic compounds. We're going to switch gears a little bit. Here, problem 4-ish approximately, right? So, and we are going to take a look at, and then, yeah, also here, take a look at the backwards situation, right? So, for example, if you have a polymer like that, so let's see. So polymer, yeah, this one. So let's say, imagine you are going to have a polymer which looks something like this, CH2, CH, CH, and then let's say we're going to have the famous aromatic ring, famous benzene ring, right? So here, so I think we talked about this earlier. So, but if you look at this thing, right, it's going to be nothing more than C6H5, right, which is also going to be called, also known as a phenyl. So it's often designated as PH, right? Phenyl. Phenyl is the name of this substituent, the C6H5, right? So it's basically a derivative or a substituent which was derived from benzene, right? Benzene is C6H6. Here, if you look at this compound, right, it's nothing more than C6H5. Here, this carbon just has like 4 valences, right? And it has now connection to another carbon. So instead of the H, which was possessed previously by this carbon in the benzene molecule, once H was removed, we make C6H5, which is going to be known as the phenyl substituent group, right? So here we go. So we have the monomer like that. So let's say n parts of that, right? So then what happened, right? So what's the reactant? So this is a polymer, right? So here you go. So you have this kind of like parenthesis, right? And then n. So n can be kind of like specified somewhere. Maybe somebody says it's n equals, I don't know, 1,000, right? So then you can say, okay, well, we have 1,000 of those pieces. So it looks like a polymer. So because polymers are supposed to have like broadly a lot, right? A lot, like a high number relatively of the of those like repeating units, right? So like this thing will be repeated basically. So and then those like factors, the fact that you have like n being kind of a large number relatively, and you have this thing in parentheses, and then this implies that this thing CH2CH phenyl is repeated like n times, right? Maybe 100 times. So this will all kind of like tell you that look at this, I'm a polymer, right? So that's going to be your polymer. So, and then also we see the single bond typically. So for our kind of like at our like level right now, so we were going from the double bonded alkene. Obviously, alkenes have to have a double bond, right? So we were going to the like alkane, long alkene chain with maybe some substituents that not necessarily Okay, so let's see, whiteboard, share. Okay, so looks like we are back and the recording still continues. All right, so there was a little bit of a technical hiccup because the battery died. So, but anyway, so this is our stuff, right? So then let's say that's going to be our polymer right here, right? And so yeah, that's going to be our polymer right here. So this one. Okay, so now what is going to happen is that let's see what is the monomer, right? So it could be like the reverse question. So remember, we were trying to highlight the electrons in the red color, for example, like so, right? Well, that's not what I wanted, but yeah, it's okay. So these are the electrons, right? So from those covalent bonds, which used to be the pi bond, by the way, right? So now just connect them back into the pi bond and show the monomer, right, which is formed. So we are going to have n particles, right, of the n molecules of the monomer, n, whatever number is, right, and then we'll show the monomer. So which is going to be like CH2, CH, just kind of like copy the repeat unit, right? The repeat unit is a synonym to the monomer, and show everything else which is supposed to be there, right? So the substituents, like in the like alkene, so right now we like don't touch them, so they can be like different things, right? Maybe just a methyl, maybe it's going to be like phenyl group, maybe it's going to be some sort of halogens, so the options are plentiful, right? So because conceivably people want to have like different structures of the polymer, right, chemically, and depending on the chemical structure, you can have like different like physical properties, maybe like different, I don't know, toughness of the resulting material, right? So different flexibility, brittleness, and so on, right? So then this is your bond here, and now you have those like red electrons that form back, right? So the pi bond, which you break to make the polymer, right? So that's it. So CH double bond, CH with a double bond and single bond, everything seems legit. And molecules of this kind are connected. So N monomers. So this is going to be your monomer, CH2 double bond CH phenyl ring, right? So phenyl group. So, and that's it. So that's your monomer. And then once the reaction happens under like certain conditions of polymerization, we're going to form these repeat units, 100, like n number of them, some number n, like 100, right? N. So, and then, yeah, what's going to be happening is that bond, that gray bond will be broken in order to like make new covalent bonds between the repeat units. So, yeah, that's our stuff for now. So now let's take a look at some aromatic compounds, right? So here we go. We're going to switch gears dramatically, and I'm going to clear everything. So here we go. So P, whatever, maybe like 5 or something like that, right? So maybe 4, so but doesn't really matter. So here we go. So we're going to take a look at some aromatic compounds, right? And then we'll just recall their structures and try to name them, right? So that's where we're going to be. So aromatic compounds have to have some kind of like distinct features, such as a 6-membered ring, right? So made of carbons and hydrogens. So then we have the like alternating double bonds, like so. So that's a benzene, right? So C6H6. So again, that's a skeletal structure or line angle structure, right? So, but by our conventions, you need to like know that there is going to be a certain number of carbons and hydrogens, right? You can write them out for your practice. I'm going to go full screen. Okay, so yeah, so and now, so what happens is that from C6H6, that's a pretty like boring molecule, so we can go to like different substituted benzenes, such as this one, right? So as I draw that, so it should ring some bells. So what's the name? It's aniline, right? So aniline will be looking like this. And now let's say we're going to have more substitution, like so, right? So let's like take a look at this molecule. Okay, so that's the one, carbon, carbon, another line angle structure, right? So then if you want to name it, so let's throw the base name, first So it's going to be like an aniline, right? So because of this kind of like phenyl ring or benzene ring, right? So benzene ring substituted with NH2, we're going to have like aniline as part of our name. Then in turn, the aniline is substituted in the benzene ring, right? So because now here, so if you look at aniline, right, it used to be like this. So that's your like aniline structure, C6H5 NH2, right? So now you here have theoretically your H, right? So, but now here, if you look at this, 1, 2, 3, 4, 4 single bonds on this carbon right here, right? So now it must not have any H's. So that H basically was cut off, right? And then substituted with what? With this group, right? So this is CH2, CH2, CH3, nothing more than propyl, right? Or N-propyl. So as we can call it sometimes, signifying that it's just going to be like a straight chain substituent, which was derived from propane, right? So, and then here we need to name or number the carbons rather. So where the substituent is attached, that is related to the kind of the to the accepted name, common name, right? That carbon will bear number 1, right? So then we're going to go down from it this way or that way to minimize the numbers. But if you go like clockwise, counterclockwise, this substituent will end up on carbon number 4. 1, 2, 3, 4, 5, 6. Yeah, or 1, 2, 3, 4, still 4, right? So it doesn't matter. So where you go. So it's going to be still like a 4, right? So it's going to be like a 4 propyl. So 4 propyl aniline, right? So in other words, so we can also notice that this substituent is positioned in the ortho position relative to the nitrogen, relative to NH2 group, basically. So no, not ortho, sorry, para, because 1,4 substitution pattern in terms of like double di-substituted benzenes is going to result into the para designation, right? So we can also call it para, P for para propyl aniline, right? Aniline. So then like both of them will kind of give you the same result, right? So you can imagine aniline, right? So where N is attached like to the benzene ring in aniline. So that carbon that bears the like CN bond, right, with the nitrogen like from the like aniline molecule, basically. So that carbon will have number 1, right? So then 4, okay, we're gonna go down like to carbon number 4, starting with carbon number 1. So in carbon number 4, right, in the benzene ring, so we will have the propyl attachment, or carbon 4 will bear the propyl group. Or in other words, so like para stands for like 1,4 substitution. Carbon number 1 obviously will be still having the NH2 group. Carbon number 4, right? So we'll be having the propyl group. So to say that there is propyl in position number 4, we can use the designation para. So that's also fine, right? So if you have maybe some other situations such as like this one, so let's say you have something else, right? So let's maybe switch gears a little bit, and we are going to have here maybe, let's say, I don't know, like COOH, right? So that's going to be our benzoic acid now. So then maybe let's say it has a fluorine here, right? So in this case, fluorine is going to be in position number 2, right? As you might guess, 1, 2. That's a 2 right here. So, and as a result, what we are going to do is have something else, right? We're going to have another molecule here. So on one hand, in terms of numbers, right, we are going to have 2-fluoro benzoic acid. So there's going to be like the space. So 2-fluorobenzoic acid, right? Or we can also call it, so since we have a 1,2 substitution pattern, right? So we can also call it ortho fluoro benzoic acid, right? So yeah, we can basically use sometimes those things interchangeably. 2-fluorobenzoic acid, orthofluorobenzoic acid, right? So we can also, it's basically, it is two ways to show that in position 2, right, there is going to be F. So position number 1 will be occupied by the COOH from the benzoic acid, because like by convention, where the substituent is in the kind of like common named compound, right? So that carbon will have number 1, right? So everything else is counted after that carbon. So carbon number 2 will contain the fluorine group. So now let's take a look at some more examples. So, and then at the same time, we're trying to go over like different common names, right? Which we have seen so far. We saw like aniline, that's that structure, right? We saw the benzoic acid. It's like this one. So here we have the substituted benzoic acid, right? So, but it's possible to have the substitution. That's what the chemistry is about to a large extent, right? Like making like new compounds with new properties for like new applications. So then we also have toluene, which is basically C6H5 with CH3 or the methyl group attached to that. And finally, we have the phenol. So it's probably going to be a little bit more exciting than the good old toluene, right? So phenol will look like this. So that is a kind of alcohol as well, right? So, but here we have the attachment of the OH to the aromatic ring, right, as we call it, this C6H5. So then that's going to be our phenol, and let's say it has the bromine here, right? So this one is going to be, again, so where the OH group is attached in the compound with a common name, right, of phenol in this case. So that carbon will bear number 1, right? So then carbon number 2 will count this way, and carbon number 3 will be this way. So if we can theoretically go here in this case counterclockwise and count the carbons. Let's just do this verbally. 1, 2, 3, 4, 5, right? So in this case, bromine will be on carbon number 5 as opposed to carbon number 3. So, but we want to minimize the numbers that signify where the substituents are attached, right? So then we are going to go with the clockwise counting in this case, right? So, because in this case, if we go clockwise, we are going to have the bromine in position number 3. If we go counterclockwise, the bromine will be in position number 5, right? So, which is like a higher number, and it loses. So, consequently, this guy so will be called the 3-bromophenol, right? 3-bromophenol, or maybe it's going to be called also meta, right? So finally, we have this meta M, right, from meta. So if we have the 1,3 substitution pattern, then we are going to deal with the meta substitution in case of di-substituted benzenes. So because 3-bromophenol is a di-substituted benzyl, no, di-substituted benzene, if you look at this, right? So we have like H removed, switch to H, and another H was removed and switched to bromo group. So di-substitution. So meta, bromo, sorry for my handwriting, phenol, right? So this will imply that we have the 1,3 substitution. Position 1 will be for the OH from the phenol, right? So that's our base name from which we start naming and drawing, right? So if needed, and then in the meta or the 3 position relative to like OH in position 1, we will have the bromo group, right? So 1,3 or meta in other words. So yeah, what else? So maybe some more substitution patterns. Let's take a look at tri-substituted benzenes. Erase everything. This will be a continuation of like P5, I would say. Problem 5-ish. Okay, this one. We're going to get back to our benzoic acid. can show the functional group, right? So that's going to be a good idea because later on we'll be able to kind of use this kind of like thing, right, in order to see, for example, how the benzoic acid can make ions, right? So because, and then here we'll jump into that, right? So after we name it, so basically here you have, let's say, bromo group and another bromo group, right? So here you can recognize that there is a benzoic acid part, right? So it's like benzene ring with the COH. That's going to be our benzoic acid. Then it's substituted in the benzene ring using two bromo groups, right? So where the COH functional group is attached in the common name, all right, so in the common structure, such as the benzoic acid in our case, so this carbon will have number 1, right? So then we can start naming or numbering carbons, and we can go basically like two ways here, right? So clockwise or counterclockwise. So if you think about it, if we go clockwise, we'll get to numbers 2 and 4, right? So 4, where our substituents are. If we go counterclockwise, let's just do it verbally, we're going to go like this: 1, 2, 3, 4, 5, 6. So counterclockwise, we'll get 4 and 6, right? So apparently they will be higher numbers than the set 2 and 4, right? So consequently, our number in clockwise will win in this like naming process, right? So we'll have the benzoic acid. So because we can see the benzoic acid like backbone here, essentially. So let's put it down, benzoic acid. So then this acid is clearly substituted with the two bromo groups, right? So, and then they are in positions 2 and 4, right? So carbons 2 and 4 will have a total of 2 bromo groups, dibromo, like similar to what we saw, right? So basically we have the bromo groups, right? So that's one part. Then di means that there are 2 of them total, and then they are amongst carbons 2 and 4, right? So 1 on 2, 1 on 4. There are no other options, right? You cannot attach somehow 2 bromines to this carbon 4, for example, because it will become a pentavalent carbon, right? So we kind of like need to sort of like be constrained, right, by the rules. So that's why like we like ask those questions. Oh, how many bonds can a carbon make, right? Things like that. So 2,4-dibromo benzoic acid will be formed as a result here. So yeah, that's the one. So, and here we go. So yeah, that's going to be our di-substituted benzoic acid and tri-substituted benzene molecule in general. So now maybe like one more topic to look at is here we have this nice segue into the ionization, right? So that's going to be this like OH bond will be broken, right? So acids, so like still benzoic acid derivatives can show the like acidic behavior, right? Which is kind of like the loss or the production of the H plus, right? So this is something that we can show also in alcohols. This is going to be something like as a food for the thought, right? So don't worry about that. So, but think about what acids do, right? So it's like by no means the topic for like our, let's say, like upcoming exam, if you think about the like exam topics, right? So based on this video. So, but in general, that's a good idea to think about it, right? So, and then this also can be encountered, guess where? In the light of alcohols. So alcohols are molecules which contain the, like a COH functional group, looking like that, right? And then, yeah, we can theoretically have like lots of things attached in turn to this carbon, right? So typically we start with something kind of like based off of alkenes, maybe like this. So let's say that's going to be our propanol, right? So here we have the 1, 2, 3, 3 carbons. It's a propane as the alkene foundational compound, right? So, but then we basically switch one of the H's, one of the 8 H's of alkene to the OH group, right? And then we have this COH pattern, which signifies the alcohol. So that's going to be our alcohol, right? So we can also call it, right? So we didn't look at the nomenclature yet in our presentations. So, but here, so like think about it, right? So like how they are named, right? So they're named off the carbon chain, right? So here it's going to be like propane, right? And then we'll use this propan part as the root part, right? So in our name. So this one will be like also containing for if you just listen to the word alcohol, right? So it has this OL part on that, which is translated into the official names of various alcohols. So here we'll have the propanol, right? So theoretically, this OH group can be on carbon 1, on carbon 2. This is again carbon number 1, right? So like these terminal carbons are kind of equivalent, right? In terms of when an OH group is attached to like either of them. So, but what's going to be unique is that if you put the OH group into the middle carbon, right? So then theoretically you can have like two kinds of propanol, right? So one of them will be like this carbon or that carbon. When you put OH, you'll have the same identical compound, right? So then it's just a matter of like showing that, right? So this way or the other way. So, but you'll get the same compound. When you are not going to get the same compound is that when you get the OH in the middle carbon, right? So that's going to be your structure here. Then beef it up with hydrogens. And you have like one propanol, it's literally attached to carbon number 1, right? Lowest number. So you have like one propanol. So as opposed to 1, 2, 3, 3 propanol, right? So that's going to be a higher number for the where the substituent OH is attached, right? So one carbon will bear the ol or the OH group, as we earlier talked about that, right? So like OH group will be on carbon number 1 in the like propane-based backbone, right? So here we go. So this is going to be 1, 2, 3, 1, 2, 3. So either way, so on carbon number 2, we have the OH group, right? So what's going to be the difference in the name? It's going to be like that, right? So we'll still have the like propane, right? So, but as our backbone, so propan, right? Since it's an alcohol, it will have the suffix OL, right? And then 2 will signify that this like OL, which in turn means the OH group, right? Which will be attached to carbon number 2. On carbon number 2, we'll have the OL or the OH group structurally, and then we're going to have total, the name will be sounding like 2-propanol, right? So again, it's based on propane. So on carbon number 2, there is the OL. OL means OH. So, and then you can like unravel this for like many other alcohols, so which we'll have examples of. So yeah, if you look at the alcoholic structure, so yeah, maybe some kind of like previously known terms, don't have to like redraw that. So it's going to be the Lewis structure, right? So for the Lewis structure, it's going to be a good idea to recall your long pairs. So oxygen makes in organic chemistry 2 bonds, right? So it could be either 2 single bonds, which is going to be the case in alcohols, by the way, right? So in some other cases, oxygen can make double bond, right? Such as like carbonyls. So, but it's going to be another topic already. In alcohols, oxygen has 2 single bonds, 1 to carbon, 1 to H, right? So then what happens next is that we can show the Lewis structure. Okay, all good. So now something to like think about is the physical properties, right? So that's like where we start before we go to reactions, because it's going to be more complicated. So physical properties, if you look at the alcohol and compare it with the water molecule, right, you will see a good degree of similarities, right? Why is that so? Because you have this OH group in the water, you have also the OH group in the alcohol, right? Which means they will be kind of like one another, right? And then it means if you like try to mix them, right, so you will have the miscible mixture, right? So, or in other words, you could say that the alcohol will be likely miscible with water, which is going to be confirmed by experiments. If you literally mix the alcohol and water, so they will be mixed together, so they will be miscible, they will form the uniform mixture, not like 2 layers, right, whereby one compound floats on top of another, right? So that will be like immiscible situation. So, but alcohols and water so oftentimes are combined, right? So very nicely, and then they make the miscible mixture because of the presence of this OH groups, which first of all provides likeness, right? And second of all, it could also make the hydrogen bonds, right? So the hydrogen bonds between like H of the alcohol and oxygen of the water, for example, will make the hydrogen bonding, right? So which will lead in turn to the solution formation, right? So the intermolecular forces will facilitate the kind of formation of the solution, right? So because they will let the molecules bind and stay together, right? So that's what a solution is about to an extent. So yeah, that's going to be kind of like our situation here. So a bonus thing, so just kind of in terms of the like moving on towards chemical properties, right? So chemistry is about reactions. Reactions are, like in particular, are about bond breaking, right, and bond formation. So here, let's redraw the alcohol and show its acidic structure, right? So here again, you have some kind of like terms, right? Okay, acidic structure, what does it mean, right? Or acidic behavior, rather. So in this regard, so it means the loss of H plus. What's H plus? That's a proton, right? So where can we lose it? So we can previously know that CH bonds are considered nonpolar, right? So they will kind of like stay put, right? So if we want to say, well, how does dissociation of the alcohol happen, right? So it turns out that the CO bond is pretty strong, right? So this bond also does not dissociate. Plus, if you think about the breaking of the carbon-oxygen bond, it will not give you the necessary thing for the acidity. For the acidity, we must produce the H plus proton. If you try to break CO bond, you'll produce, in this case, propyl, right, part, CH3, CH2, CH2, and OH, which are not, neither of them is H plus, right? So by the look of them. So consequently, your only option here is not to break the O carbon bond, but OH bond. So if you think about that, this will give you, upon the breaking, H, right? So, and then H is very close to H plus. What's going to happen? Indeed, you are going to produce H plus because of this situation, right? So previously, the kind of like brings us back to lecture number 1, as a matter of fact. So yeah, you like do have experience with the proton transfer, right? So, and the formation of the H plus. So because of the first lecture, if you were there and if you remember that, hopefully. But anyway, so here's a bonus point kind of like situation for you. So here previously we used to have 0 charge on oxygen, 0 charge on H, right? That is just like 2 neutrally charged atoms which make a bond, right? So that can happen in HH situation, right? For example, like 2 atoms of hydrogen make the hydrogen molecule, right? So here's just like 1 hydrogen atom and then this like oxygen atom from the like this big part, right? So that contains oxygen atom and like CH2 and stuff like that, right? So now they kind of like redistribute the electrons, and then how does it happen? It's because the oxygen is more electronegative, in it will force, it will pull the electrons towards itself. So we can show it with this kind of like arrow, which shows the moving of the bond entirely of the like couple of electrons towards the oxygen. As a result, you are going to have the following. So first of all, redraw the things not to lose any like atoms, right? Because we need to have the balanced equation. So we have our oxygen, right? So we can show those electrons in a different color as well. Yeah, here. So red and red. So keep an eye on those. Red, just 1, right? When it's like that, oxygen is still 0 charge. Charge of an electron is -1, right? So now we said that the oxygen pulls both electrons toward itself. And that's what we're going to show, right? So now they're both on the oxygen. So now the oxygen will have to have the charge of -1 because the electron, this one, is minus, right? Negatively charged. 0 and -1 from the electron becomes total, brings about the negative -1 charge on the oxygen. What happened to the H? So H used to be the neutrally charged, okay, but now it lost 1 electron, right? So if you think about that, the neutrally charged H lost an electron, right? So, but it has to produce the counter to that. The counter will be the generation of the positive charge. You lose -1, then you produce +1, and then you make nothing more than your proton, right? So, which is what we need to have in acids. H plus, right? So because acids are proton donors, so they lose a proton, right? So as we say, so, and then here we have this acidic behavior exhibited by an alcohol, right? So yeah, that's like your thing here. So proton transfer, maybe a little bit advanced to some of us, but here we go. So yeah, another exposure to that. And that's a good thing to keep in mind. So because this like proton like making situation will be happening like a lot in like various real life situations where, let's say, alcohols are concerned. Maybe it's their metabolism. So oftentimes you can hear, okay, alcohol is acidic. So consequently, like what does it mean, right? So it produces H plus, right? And then this is kind of like not necessarily like a good thing for the like stomach lining, for example, like if you think about that from the medical perspective, because like the overconsumption of, let's say, like alcohol can produce like a lot of H plus. H plus again like is a like relatively in high amounts. It's a harmful agent for the like stomach lining, which will lead to like its irritation and potential like tumor, or like rather what's it called, the like hole in the stomach formation type of deal. So yeah, I forgot what it's called medically, but it's again something that is about dependent on this like proton formation, and now you can like know how the like alcohol delivers the proton, right? So yeah, and just like try to like tie those things into like some like bigger ones, like small building blocks lead to kind of like further like advanced conclusions. So and here it goes. So I think it's about time to conclude. And yeah, thank you for your attention and have a good time, everybody. Bye. You're welcome. Right, stop recording.